Welcome to May 13th LeetCode Challenge, populating next right pointers in each node 2. Given a binary tree, you have the following struct node with an integer val, a node pointer left, a node pointer right, and node pointer next node. Populate each next pointer to point to its next right node. If there's no next right node, the next pointer should be set to null. Initially, all next pointers are set to null. So we're given this binary tree here, and we want to basically point all the next right pointer to its value. If there's no next right pointer value, then there is point to null. So for instance, you take the first level, right? The first height of the tree, 1 points to null because there's nothing to the right of that. 2 points to 3 because 2 is to the right of 3, and 3 there's nothing to the right, so points to null. And then lastwise, the third layer down, you have 4 points to 5, points to 7, points to null. So that's pretty much how you define it as here. If you have an empty node, an empty binary tree, then you would output an empty list, basically. And the constraints of the number of the nodes in the tree in this range is between 0 to 6,000. The value of each node is between -100 to 100. And some follow-up questions saying that you may only use constant extra space. Recursive approach is fine. You may use implicit stack. Does not count towards an extra space for this problem. So yeah, you could definitely use a recursive approach for that as well. But I think using a breadth first search using a stack will be the best. Well, I mean, it'll be a solution, right? So, define a stack and put root inside while stack exists. What we're going to do is find the length of the stack, and then we also have to loop through the length of stack. So for each index in the range of n, let's say, what we could do is we could actually, you don't need to do this, we could just directly put this inside range length stack, just to save us one extra space there. Alright, for each of that, what we want to do is update a variable called node, and we want to actually pop it from the first index of the node, so pop 0. Alright, now we have the node, so if node is none, so if the node has no value to it, then we can continue, is none. Then we continue from that count, from that node. Just bypass this. Next, if, oh, never mind, I need that back. And assign to that. So if the index we're at is less than n minus 1 values of the length of the stack, then what we want to do is update the node, next node, node.next, to be stack at the index 0. Right, that means this is the first element of the stack we add onto it, so therefore there is a value afterwards, right, to the right, I should say. So if next thing we need to do is basically iterate the left side and then the right side, so we'll have to add to our stack. So basically what we do is node.left exists, so there is a left node to it, then pointed to the left node, I should say, then we append that value, not that value, that node, append that node, node.left, to the stack, and then if we have a node.right exists, then we also append that to the stack as well. So appending all values to the stack, node.right. Append both the left and the right side to the stack, and then we basically iterate through. If node is none, then continue. If there's next right node, then we just basically point it to the next node. Ideally, all of it, initially all pointers are point to null, set to null, so therefore we don't have to worry about the last pointer. And we exit this loop, the for loop, exit the while loop as well. Then we essentially should be able to return root, and that should give us our answer. Hopefully. Alright, that looks reasonable. And we know that we build our stack, accepted, awesome. we build our stack and using n values, so that's the length of our stack. So in terms of time complexity, it's big O of n. For n is a value, for n is each node of your root. And in terms of space complexity, it's actually big O of the largest width. So space complexity meaning that, for instance, if you have for each the largest width of the tree. So basically, for example 1 here, you have 1, 2, 3, essentially, or 4. I mean, it's basically n plus 1 types of so it's the largest width of the tree is the memory complexity, and that is it. That's all. Have a great day, guys.